Hello everyone. My name is Agha Ali Haider Kizilbash. Welcome to my talk. My talk will be on Ant colony optimization based multi-robot planner for combined task allocation and pathfinding. We are very inspired by all the multiple mobile robots that are being employed in factories and logistics environment nowadays, in material handling, warehouse applications. And what we saw that there is a problem that a lot of in a lot of scenarios, a lot of multiple mobile robots need to do some tasks, so assign tasks to themselves, and tasks are like pick up and drop of an object nature. And they also need to find paths to their tasks, which are of course collision free. And they have to do this simultaneously. This is where our research is, and we would like to come up with a heuristic approach to solving this combined problem. So here, our research is on ant colony optimization, which is a heuristic approach based multi-robot planner, which we are going to prepare for combined problem, which is combined task allocation and pathfinding. I would like to summarize these words, go on saying that the goals of the research are that what we want is we want minimal total distance to be covered by all the robots. We want some nature inspired simple rule because individually task allocation and pathfinding, the two problems that we're addressing, are both itself NP hard problems in computer science. So that makes to find a solution exponentially very expensive. And therefore, we would like a heuristic approach, a simple rules approach. Therefore, we will try using end-colony optimization in this, which is itself very successful in solving the individual problems individually. Also, we have an already existing planner in front of our APA, which I will also talk about. We will try to improve that. Let me start with the state of the conflict-based search is very common solution for these combined problems, which is used a lot. ECBS, which is employed by, which is in works with the Amazon Robotics. TCBS is task waiting CBS, which caters also that tasks should be completed well in time. Uh, and I will be using TCBS also in comparison with the planner that we will be making. There's also some work from these authors on ant colony optimization using for a similar problem, which says that the robots should be treated as ants, and they start from one position, all of them, and then the first tasks are assigned at random. So this is not something that I will be doing. It's our research is on different part that we already talked about, and I would like to show what the ant colony optimization is based on. It's based on the foraging behavior of ants, where ants go out in search of food, and then they take decisions to different paths, and then how they take decision is based on randomness and pheromones. Pheromones is just a smell they leave while traveling, so that the other ants that are coming can decide or take decisions based on pheromone and randomness. The more pheromone, the more it is likely for ants to go there. So eventually what happens is by depositing these pheromones, finally ending up with the shortest path having the stronger pheromone. And that becomes the usual path for the coming ants. Now I would like to talk about my planner. The planner that we have worked on, we would like to call it ACTF. And the simple structure of this planner is that we will take some jobs, some pickup and drop off locations, some agents, or robot starting position. They can be really arbitrary wherever they start from. Then there is an environment, a grid map. What this planner would be providing is some task assignments, some respective task assignments to robots, and of course the paths to those tasks, collision-free paths, optimizing for total distance, of course. Then I would like to show the pseudo algorithm, but then I would like to talk using this flowchart and try to explain that how this works, how our planner has worked. So until all tasks are assigned, we would take all the robots and spawn a set of ants from that particular robot. And then the ants go to all the tasks, calculate probabilities based on randomness and pheromones, and then they select those tasks, they move, they update the pheromone, they visit all the tasks, and then they get reset. After that, for every robot, it updates the pheromone of its own set using its own set of ants that travel from the robot. And then it makes a pheromone map for all the tasks. If there is a very granted advantage, a clear advantage of a task over a robot, it gets assigned and then it moves further on. If it is not, then it is not necessarily assigned. Uh, and then when all tasks are assigned, the secondary collision checks are done, best selection is checked, and then we reset robots to the starting positions. This is one iteration. Iterations are kept very independent so that the more iteration, it's just going to increase the increase the computation time in a linear manner. And we can have a lot of iterations because these are totally independent. We can have different results and then compare which ones are better. Moving on, we would like to talk about some results. Some comparative results. So this is a case setting, a normal case setting that we have a grid map of some black obstacles that we have. Some orange circle robots and the green triangles are the task that needs to be done. The arrow directs to where the task need to be put. I will be using three planners: ACTF, which is our research planner, the greedy planner, which assigns the most nearest task to the robot, and TCVS planner, which also caters to the task waiting time and use a CVS approach for assigning tasks and for pathfinding. We have evaluated against these parameters, but you can find more information in the paper. No, first comparison I would just like to do with the greedy planner and the ACTF error planner, and you can see that there is a whopping amount of TD, the total distance saved by using the ACTF planner. So there's a whopping amount of 34 travel distance units saved using the ACTF planner in regards to the greedy planner. Another example that this is a sort of a logistic type of environment, or if you're from Germany, this is just a map of a normal Kaufland where you get lost every time. Uh, so in here, I've compared all these three planners, and here also you can see that the total distance that ECTF, our planner, provides is very less than all the others. For example, a very homogeneous example I will take now. Why? Because this you can even assign it yourself right now. It's very homogeneous. It's very simple one path problem, and you can see that here all the fun thing is all the planners gave a different assignment. The greedy planner said the first robot should do the first task because nearest, yes, greedy. The second robot should do the second task. Okay, TCBS said, okay, no, the second should do the first one, the first should do the second task. Okay, ACTF said, okay, no, the second robot doesn't even need to move. The first robot can do the first task and then the second task and still save a lot travel distance. And that is where the ACTF excels. This we will also talk and discuss. Now, some conclusion. So these were our goals of the research that I initially pointed out. And with regards to that, we have seen that we have empty assignments that I just shown you, that our planner also suggests that there are some robots that don't even need to move to complete all the tasks and still save a lot of total minimal distance. Uh, and then there is a granted advantage that is clearly variable, so you can control the robustness of whole algorithm with this. Quick computation, we wanted a quick computation based on some heuristic or nature inspired rules, and that we have achieved. And the comparison is really promising, which brings to the future works. The future works that we are thinking is, first of all, multi-objective optimization. We've already talked about there is one more objective that we have catered at TCBS, which is task weighting. We would like to include that in our planner as well. And we are also working on fleet management projects in Fraunhofer IPA. So we would like to apply this planner in our fleet management. These are direct references that I used in my presentation. And I thank you all right now. And I would like to also thank Fraunhofer IPA for funding this project, for funding this research, Universidad Magdeburg for funding this, for collaborating with us, and the authors and the co-authors and the supervisor. Thank you very much. We can have questions now.